Hello everyone, my name is Arnav Sharma. I am pursuing BS in Data Science and AI from IIT Guwahati, and today I will be presenting my term project on the topic Plant Disease Classification using Vision Transformers in GradCam for the course code DA378. The objective of this project was to develop an intelligent system that can automatically identify diseases from plant leaf images while also explaining how the prediction was made. Along with the deep learning model, I also developed a GUI that allows users to upload an image and receive the disease prediction together with the visual explanation. In this presentation, I will briefly discuss the problem statement, methodology, implementation, results, and the future scope of this project. Now, plant diseases are one of the major causes of crop loss worldwide. Early detection of these diseases is important because it allows farmers to take corrective measures before the infection spreads. Traditionally, disease diagnosis depends on manual inspection by agriculture experts. However, this approach is time consuming, subjective, and not always accessible, especially in rural areas. Although modern deep learning models achieve excellent classification accuracy, most of them behave like black boxes. They simply predict the disease without providing any explanation for their decision. This lack of transparency reduces user trust, particularly in applications such as agriculture, where important decisions depend on the prediction. Therefore, the main objective of my project was to develop a system that not only classifies plant diseases accurately, but also explains why the model arrived at that prediction using RADCAM visualization. For the tools and dataset, this entire project is implemented in Python. I used PyTorch deep learning framework for model training and inference. The pre-trained vision transformer model was obtained using the TIM library, while Torch Vision was used for image pre-processing and dataset loading. OpenCV and Matplotlib were used for image processing and visualization. Scikit-learn was used to calculate evaluation metrics such as accuracy, precision, recall, and F1 score. Finally, I developed the graphical interface using custom tkinter. For training the model, I use the plant village dataset, which is publicly available benchmark dataset. It contains images of healthy and diseased plant leaves collected under controlled conditions and includes 38 different disease classes across multiple crop species. Now, this image illustrates the overall workflow of my system. The process begins with an RGB image of the plant leaf. First, the image is resized to 224 by 224 pixels and normalized so that it matches the input requirements of the pre-trained vision transformer. The processed image is then passed into the vision transformer, which predicts the disease class and also produces a confidence score indicating how certain the model is. After obtaining the prediction, GradCam is applied to generate a heat map. This heat map highlights the region of the leaf that contributed the most to the model's decision. Finally, the original image, predicted disease, confidence score, and GradCam visualization are displayed on the GUI. Now, I'll briefly explain the implementation of this project without going into every line of this code. So, this is the repository. Herein, the train.py script is used to train and load the model, and it is responsible for loading the dataset also, while and also creating a vision transformer model. After that, oh, and also the train.py script saves the best model while because my model is trained on multiple epochs. So the train.py saves the best model in this models folder so that the best model can be further used in inference and evaluation. After that, the prediction model this predict.py it loads the trained model and perform inferences on new images. The GradCam module computes the GradCam module this one the GradCam module computes gradients from the finite transformer layer and generates the heat map that explains the prediction. Finally, the app.py module. This is the GUI that combines all these components into a single desktop applications where users can upload an image and instantly receive the prediction and visualization. By separating these functionalities into different modules, my project becomes very easy to understand, maintain, and extend. It's very straightforward. Now, as for the results and outputs of my model, these two images here show the final output of the developed system, the GUI. The user first uploads a leaf image using the GUI here using this upload leaf image button. The model predicts the disease class along with its confidence score. At the same time, the GradCam generates a heat map and highlights the disease affected regions which influence the prediction. One of the main advantages of this approach is that users do not simply receive a dry prediction. Instead, they can visually verify that the model is focusing on the infected portions of the leaf rather than irrelevant background regions. This significantly improves the transparency and reliability of the system. Here are some training results. These graphs show how the model performed during training. The graph on the left represents the training and validation accuracy. We can observe that the accuracy steadily increases throughout training and eventually converges close to 100%. The graph on the right shows that the training and validation loss. As expected, both losses decrease certainly over successive epochs. Together, these graphs indicate that the model learned meaningful feature representations and converged successfully during training. Here are some evaluation metrics that I have used for standard classification. These models achieved a validation accuracy score of 99.8 to 51%. Also, the recall was 99.8 to 61%, indicating that the model successfully identified nearly all diseased samples. Finally, the F1 score, which balances precision and recall, is also 99.83% approximately. These results demonstrate that the vision transformer performs extremely well on the plant village dataset and provides reliable predictions across different disease categories. Now, although my project achieved achieved excellent results, there are some limitations to it. First one being that the plant village dataset contains images captured under controlled laboratory conditions, which with clean backgrounds and consistent lightings. Therefore, performance may decrease when the model is tested on real-world images containing complex backgrounds, varying illumination, or multiple overlapping leaves. As I had mentioned it, the single leaf is an assumption. Also, another limitation is that vision transformers require higher computational resources than lightweight convolutional neural networks, making development deployment on low-power devices more challenging. And finally, as for a conclusion, my project successfully developed an accurate and explainable plant disease classification system using vision transformers and GradCam. In addition to achieving high classification accuracy, the model also provides visual explanations that increase under trust and improve interpretability. A desktop application was developed to demonstrate the practical usability of the system. The future aspects of the system, I, I personally think that this can be extended by training on real-world agricultural images, optimizing the model using Onyx or TensorRT for faster inference, and deploying it on mobile devices for practical field applications. Thank you very much.